thank you for this opportunity to present the ongoing work around a very important topic, which is called LLM fundamentals and telecom-specific large models. So as far as I'm concerned, my name is Professor Merouane Debbah, and I'm professor at Khalifa University of Science and Technology in the UAE. And what I'm talking about is the work what we've been doing at the interface of the telecom and AI, and especially on the generative AI space. So as far as I'm concerned, I've been working basically at the interface of AI and telecom for many years. I am an IEEE RASIP and WWR fellow. And one thing which is very special about me is I've been working at the interface of industry and academia. And I think it's quite important whenever you do research to be able to understand how basically the fundamental developments that you're doing can be translated and transferred to industry. And by understanding basically, of course, the industry type of request, then you can improve on your research. And I've been doing this on a cycle, I would say, over 10 years. And I think this is the right approach to push things around research in this field. So many of the things I'll be showing are available in a series of papers co-authored with many of my colleagues. We started working basically on the Gen AI field more than 3 years ago, and roughly basically looking at the application, I would say 1.5 years ago, around the telecom. And the series of papers that are here are a series of pioneer papers which try basically, of course, to showcase the potential of using what we call large language model, and I'll explain what it is, with the telecom. We've been, of course, going a bit further than that by also looking at basically what we call AGI, which is the next step related to the domain of AI. And the series of papers also here, which are done with many of my co-authors, are also basically related to the fact that we want to bring more and more basically to the AI domain, the fact that these models should be embodied. And what we mean by that is that we want to bridge the gap between basically the digital world and the real world. And this series of papers showcase how, of course, the telecom domain could kickstart that. So that was for the introduction. Let's start directly now on the topic that are of interest for us. I think many of you basically are quite familiar with the evolution of what we call generation wireless network. And they've been going on a 10-year basis starting in 1990. The first one started with 2G, which is roughly the KPI of having what we call mobile for voice, or voice with mobility. And behind that, there's a couple of key technologies that we all know, which are basically GSM, I-75. I think it's quite important to make the difference between a technology and the KPI behind that. There are several technologies which fulfill that KPI. 10 years after, around 2000, we started building basically 3G network with the purpose of providing mobile for data. And many of you, I think, are quite familiar with the dongles which were being used in the year 2000, these USB dongles, to download a lot of data. Around 2010, we started, of course, looking at 4G network with the aim of providing mobile for internet, which is a wireless ADSL experience with mobility. Behind, of course, 4G, there's several technologies which fill that requirement. I think all of you are familiar with LTE, long-term evolution, but there's also another one which is called WiMAX, which didn't have the exact success related to that. By the way, we were so focused in building 4G with the focus around mobile for internet that on the first deployments that we did around 4G, you have to know that voice was not working quite nicely. And the reason behind is that voice in 4G is considered basically as an application. It's based on voice over LTE and other technology. And because of that, we had to work many years with a system called CS fallback, circuit switch fallback, which provided basically whenever you wanted to make a call to switch basically on a 2G, 3G network, and whenever you wanted to browse on internet, then of course you would stay on a 4G network. It was only starting the 2 years, 2016 and more, then when operators started considering shutting down a bit of the networks on 2G, that we started trying to see how we could improve the voice over LTE experience. And here, AI played a big role. Not the Gen AI, but there was a lot of innovation in trying to make voice over LTE, which is basically a bit complicated when you think about it, because it's not related to the fact that you have more bars on your phone that you're getting a higher quality, but it's related to the whole end-to-end where you have IPsec protocols. And by using AI techniques, we saw some quite nice improvements. In 2020, basically again 10 years later, we started looking at a new KPI, which is basically what we call mobile for IoT. Meaning basically being able to have the things and the IoT that you're all familiar with mobility. It turns out that the majority of networks that we are building now in 2024 are mostly providing the broadband capability of 5G and not basically the two other features, which are what we call massive machine type communication and basically ultra reliable low latency communication. And one of the reasons that, of course, we're so focused on the mobile broadband feature is that we're not able still to make money out of IoT. So there's still discussions on looking at basically the kind of revenue that we can generate from this feature. And of course, this relates, of course, to the fact that you can treat data or other types of features like localization. So in the next years, of course, a lot of work is being done to look at use cases that can generate revenues out of 5G, and 5.5G is part of that. Now, within 2030, we're looking, of course, at another feature, is basically trying to understand if the networks that we have deployed so far, especially now that we have what we call models and AI models, can provide basically the capability to connect intelligence. And we're looking for mobile for intelligence. And in that case, of course, the question arises that if the actual network 5G, 4G are capable to connect that kind of intelligence. And here I'm going to give you two examples to showcase that in general, before asking a question, you need already to deploy your new technology within the realm of basically what exists. A lot of people talk to me about massive MIMO, and I've been working a lot on massive MIMO. And they stamp massive MIMO as basically a 5G technology. But massive MIMO has nothing to do with 5G. It could be built in 4G, it could be built in 3G, it could be built in 2G. However, when you start implementing massive MIMO in 4G, you realize quite rapidly that you're limited with the kind of physical layer that you have over there and the kind of signaling, basically, kind of design that was made. In fact, if you decide to deploy massive MIMO in 4G, you will realize that you're quite limited to the number of ports due to the fact that the number of channel estimation signaling is quite limited. So we had to build basically a new kind of clean slate design, which is called New Radio, so we could push the limit, basically, of massive MIMO to what we have, basically, in the classical simulations that you do, or the theoretical limits. And it turns out that thanks to NR, we're able to push 5G to something like 128 antennas dual polarized. The same thing arises, by the way, today, when you think about large intelligent surfaces. I talk with many colleagues. They tell me that 6G is about large intelligent surfaces. Again, here, there's nothing very linking basically 6G to large intelligent surfaces. You could implement large intelligent surfaces in 5G, you can implement it in 4G, you can implement it in Wi-Fi. But here again, if you decide to deploy large intelligent surfaces in Wi-Fi or 5G, you will see that there are some limitations that are imposed by the actual signal format that does not enable you to have all that capability that you're getting out from those theoretical limits. And the question, of course, that people are trying to solve at the moment is what is the kind of standard that needs to be built to get all that potential of large intelligent surfaces. And so today, the same question arises for us also when we want to connect intelligence and trying to understand if basically the actual kind of standard that we have today in 5G is able to connect that intelligence. And I'm going to give you two examples to showcase you the transformative nature of what I'm saying. The first one basically resides roughly in basically sending information. We know that the future is going to be about what we call pervasive AI, where we're going to have intelligence at each point of the network and especially models. And roughly when you have models at each point of the network, the question is, how do you send data? Today, the way you send data, you take a video, you compress it with any kind of compression scheme or even an image, and then you send basically the compressed data on the other side, and then you decompress it. Now, if you have models on each side of the network, what you could do is do video to text, especially if you have, for example, an LLM. And then what you will send is the text, or let's say the instruction. On the other side, you'll do text to video. So with the system that I showed you right now, you'll be able to transmit data from one point to the other point, not by transmitting the data by itself, but just an instruction to reconstruct the data. And so it sounds like magic because you're able to transport a lot of information on a network by just telling how to regenerate it, basically. Now, if you do the system, there's two caveats that need to be thought about for people who are building basically the network. The first one is basically the fact that you cannot guarantee an end-to-end latency of the system. If you've been using techniques like ChatGPT, you realize quite rapidly that whenever you make a prompt to generate an image or a video, it takes a certain time. And we have a lot of requirements in telecommunication where we need to have a latency beyond a certain limit. And so you need to come up with devices which can do mobile edge generation at the speed of light or generate a number of tokens per second very fast. There's a lot of manufacturers today which are working intensively on building inference processing units which can do that. The second caveat, which is more complicated, is that if you use the system that I showed you, you'll never be able to generate the same video on each side. But when you think about it, we humans are also working in the same way, in the sense that if I ask you a question right now, you'll give me an answer with a certain formulation. If I ask you the same question in 2 hours, you'll give me the same answer, but you'll be not able to give me the same formulation in terms of text. Which means that what we're trying to build here is something of being able to provide you the meaning or the understanding and have a common understanding in the system. And so if you want to build a network on which we're connecting intelligence, we need to replicate a bit more and more how humans are behaving. And in that notion, of course, what we're seeing today in the research field is the notion of being able to build communication which are at the semantic level. This is called semantic communication. It will require basically some kind of standardization of interfaces because, of course, when the models are not the same, things get more difficult. But this gives you already an example on why you would need basically kind of new kind of approach to build those systems. The second, of course, which is more important, is, of course, the arrival of agents. And where we know in the future that the notion of apps will disappear. On different phones, you'll have what we call an AI agent or an AI assistant. And what will be communicated from one point to the other point is basically assistants which are interacting together. In the last Mobile World Congress, Dutch Telecom already made an announcement about some phones which are what we would call app-free phones. And what you want to build behind is not anymore a phone where you have 20,000 apps, but basically a large action model, meaning an interface where you talk to it, and instead of saying or typing or downloading an app like Uber, where you ask a car and buy basically the kind of subscription to it, you just say, I want to have a car in 5 minutes down my house. And that instruction, of course, will generate an action and will generate an interaction with other agents. And the question that we ask ourselves today, also in building the future, is how will this system scale with the number of agents which are interacting? And is the actual 5G layout that we have built so far sustainable in this interaction at the speed where these agents are interacting, which is not the speed at which you and me are talking? And I think these two features are quite important to understand the revolution that we're having. Now, within my course here, there's going to be two steps. The first one is going to be to give you a bit of the background, because that was the motivation, on basically what happened in 2023. And two things happened in 2023. The first one is what we call the generative AI revolution. And I'll be explaining what is Gen AI, how it works, and how it's impacting. And second, basically, is the 6G revolution, which kickstarted in 2023. And then, of course, we'll talk about the merger of these two, meaning telecom and Gen AI, and how basically it's impacting our industry in terms of development. So rapidly, and this is an example that I often give in the courses of my students, is basically the introduction about understanding the approach of data-driven approaches. So here you have to picture one of Newton, and here what we call ballistic kick. And in general, one exercise that is asked at the age of 18 is basically, I want to kick a ball at a distance d, find me the angle theta. So one of the examples that usually you do, you take Newton equation, and then you can find the angle theta with which you kick the ball. In many cases, you don't have access to Newton. Why? Because basically, well, that theory is not there, and especially for end-to-end system, we don't have that theory. So what you do to be able to kick the ball, you take a data-driven approach. Meaning you kick the ball many times, and then you put two columns, theta angle, theta angle, theta angle. And next time you're asked to kick the ball at 100 meters, for example, Well, you will go in that column of distances and check if the 100 meter is there. If 100 meter is there, then you can find the angle. This has nothing to do with AI. It's called data mining. And researchers still come up with very fast algorithm to find the number in a database. Where it gets interesting is where the distance is not there. If the distance is not there and you have 90 meters and 110 meters, then obviously what you'll do some kind of mean of the angle between the angle of 90 meter and 110 meter to find it. This is called function approximation, where you'll try to relate how distance and theta is. In fact, what you're going to do is find a function such as d is equal of f of theta. So you're going to learn that function. And to learn that function, you have to know is not an easy task. Well, what happened is that smart people came up with the fact that that function can be learned through a neural network. And in fact, you can learn nearly any function up to some conditions by a neural network. So that's a very, very strong result based on the data you have. So what I showed you here is that by using a data-driven approach, you can replace Newton equations. You can replace Maxwell equation. You measure the electrical field in the various points, and I can deduce what is going to be the value of the electrical field in other points. And you can, this way, replace many of the equations, which are the fundamental equations. So it sounds magic, but there are caveats. There are 3 caveats. The first caveat is, of course, that you need a lot of data. And we'll talk about Gen AI afterwards. What I mean by a lot of data, meaning you kick the ball many times, but imagine you kick the ball many times, you learned how to kick the ball, but then the day when you need to do it, there's wind. Then it doesn't work well. So it means that you need to kick the ball when there's a wind of 5 kilometers an hour, 10 kilometers an hour, 15 kilometers an hour. There's so many configurations that you need to learn. And it gets a lot of cost, and you need some very sophisticated algorithms to be able to do that. Second, I went quite fast, and I told you that there was a one-to-one mapping between data and distance. In fact, it's wrong. You need to know also this red arrow, which is called the initial speed, v0. So in fact, there is a mapping between theta, v0, and data and distance. So you need 3 columns, which was not obvious. It is typically the example that usually people give. You go to hospital, you have machine learning expert, or what we call data scientists. You have one column, which is what we call blood pressure, another column, which is basically cancer. And usually the doctor goes see the data scientist and tells him, hey, now that you have these 2 columns, you do some machine learning algorithm. I give you a new, basically, blood pressure. Tell me if the candidate has a cancer. It doesn't work. The question is which columns you need, and this is where you need a bit of domain expert to tell you what are all the columns which are needed, meaning temperature, blood pressure, and whatever you can do. The last also point on why we're quite limited with this approach is that whatever you kick on Earth, you'll never be able to kick on the moon. And this is called generalization. And the main reason is that you're not able to discover gravity from the techniques which are based on function approximation. So again, this has nothing to do with AI. It has to do with the techniques that we use, which are based on function approximation, how we use it. You need more advanced techniques based on topological structure to be able to discover gravity from that point, what I'm saying. Now, to do these function approximation and be able to predict, before 2017, the majority of people were using what we call natural language processing techniques for doing that, which are based on classification techniques based on statistical rules. In general, you have a bag of words, and you use a technique called word-to-vec, and whenever basically there's a man, while you're related to a king, for example, a woman is a queen, so you have a lot of different terminology, and you try to cluster them together in terms of building these things. And in general, NLP techniques before 2017 were mostly based on these neural network architecture that we're talking about. And these neural network architecture are called RNN, recurrent neural network, LSTM, GRU, and you can continue with that. The problem with the architectures that were done before 2017 is that they're based on what we call sequence-to-sequence modeling. And whenever you have something that is basically based on sequential type, it takes time to learn because you need to wait, and when you have a lot of data, it doesn't work. And in fact, we know in research that good IDs are IDs that can be parallelized. Parallelization is key. By the way, this is a general fact. If you have any kind of system that you come up with a good ID, but it can only work for 1, 2, 3 devices, but it cannot work for more, then it's not a good ID. The same thing in business, by the way. If you have a business that is running, but you can only serve 1 customer, 2 customers, but whenever you have 10 customers, it doesn't work, it's not a good, basically, type of system that you're working. So parallelization is key, and these were not able to parallelize. Second, of course, they cannot learn long dependencies. And if you have been using ChatGPT, you've been seeing basically the kind of long sentences that you can have. And so these were the big problems that we had in the pre-2017 era. And then basically in 2017, a key paper appeared. The key paper is called Attention is All You Need. By the way, today if you go to conferences, there's many papers which are finishing by is all you need. Addition is all you need, compute is all you need, whatever is all you need. And this is, of course, reminiscent of that paper of 2017. That paper of 2017 was published by people from Google Brain, University of Toronto. And you have to know that this is one of the papers which is the most highly cited. I haven't checked quite recently, but I think it must go around 150,000 to 200,000 citations, just to give you a clue on how important it is. So what's key about that paper? Well, they propose an architecture which solves exactly the 2 caveats I was talking about. The fact that you can come up with an architecture which is parallelizable, so you can learn in a time which is reasonable, you're not taking years, and this is very key today. And second, it can learn long dependencies. And that architecture is called the transformer architecture. And by the way, when we talk about GPT, the T that is in GPT is transformer, and GPT means generative pre-trained transformer. But how is this related to LLM? How is this related to LLM? And what do we mean by modeling a language? Well, it's all about basically modeling a conditional property distribution. So here you have a sentence where I write the capital of the United Arab Emirates is Abu, and I need to find or predict the next word. In fact, we'll see it's about predicting the next token, because a word by itself, it really depends on the kind of language that you're doing. So how are you going to be able to predict the next X? Well, what you do in general for doing that, you will compute what is the probability that X is equal to Paris, knowing that the capital of the United Arab Emirates is Abu. What is the probability that X is equal to Dhabi, knowing that the capital of the United Arab Emirates is Abu? So if you had been able to learn this function, and you had it, then what you do, you compute all the possible X's, you take the most likely, and then you put it there. Okay? Once you've found this X, this becomes your new context that you put here, and then you look at all the different properties for the next X1. And you go on like that, and you can generate a full text. This is what we call generative AI. I can do all the text, and I can fill you a paper by doing this thing. I can fill you a book by doing this technique. If I could know this conditional property distribution, if I could learn it, okay? In fact, doing these decisions which are hard, meaning taking the most likely and putting it here and then putting it back, can create basically some issues which are called hallucination, because if you make a wrong decision, then of course it translates after to many. So of course the best way to do it would be to learn the trajectory, meaning what is the probability that x1, x2, xn, which all the probable texts that you have. We don't do that because it becomes too complicated, which for my communication, of course, colleagues, could be a good research topic, because you could build up maybe some kind of Viterbi algorithm for this, because you have a lot of branches and you go on like this, but we don't do it because from a computational perspective, from a storage perspective, it gets totally crazy. But this is exactly how it works. Now the question you can ask me is, how do we learn this thing? Well, learning this thing is very easy because you're going to do a function approximation. So if you had no knowledge about machine learning, property of x, knowing the context, which is this function, well, if I was at school, I would say this is a polynomial. I would say this is a0 plus a1x plus a2x squared and an xn. N is the degree of my polynomial. A0 to an are what we call the weights. Learning basically the polynomial, you just do minimization of a quadratic error, or whatever error you want. You have a lot of data, and then you can identify all those parameters. Clear? Now, if you decide to do a polynomial approximation and learn those weights, it's not basically an algorithm or basically an architecture that scales. It turns out that to do that, what we do is exactly what that paper was doing. You will look at an architecture which enables you, of course, to parallelize that learning, and it turns out that the transformer turns out to be the right one. Second also, which is very nice about this approach, is that it is basically a self-supervised learning problem, and not basically a supervised one which requests to label all the data over there. And I think that was key in pushing it. Of course, today, the majority of people who are working on this are using this approach that I showed you here based on what we call a GPT-type architecture, which is a decoder only. You have to know, of course, that there are others, like encoder, decoder, the T5, or the prefix LM, which is an encoder only, and the majority are still using that kind of approach to build basically their model. And of course, how it works? Well, it works according to this approach here. In general, you have a text, a language, which could be any kind of language, Arabic, English. And then you need basically to do a representation of that language through a tokenizer, because each language can be represented differently. And the tokenizer is key here, because depending on the language, you will choose a different tokenizer to express what we call a token. A token is the least representation of your alphabet, in some sense. Then you do a system called embedding. From an embedding, you go through a transformer. Then basically, you have an embedding plus softmax. You do your sampling. And then basically, of course, up you go back to, as we said, predicting. You put it in the context and you go on. And so this is how the system works and the architecture works. So although it seems easy, in general, you have to know that one of the key aspects of this approach is the fact that you're running these things on a lot of GPUs. And being able to run this kind of architecture on many GPUs is what I call engineering art. Engineering art in the sense that the more you scale the problem in terms of training, the more, of course, you have issues with the fact that some GPUs burn and stuff like that. So the key is, of course, in being able to run this system at a large scale. Of course, building those systems and models based on the approach that I showed you here requires compute. And compute, you have to know, is not easy in the sense that in general, it costs you a lot of money. The kind of budgets that people are talking about, at least this year, is roughly something like 100,000 GPUs, H100. So you can imagine basically the cost today of building this model. And only a number of happy few can afford basically that number of GPUs. And you have to know that the models that we're building have also sizes which are extremely high. I'm giving you here what was happening in 2021, and I'll explain why now we're running into sizes which are much smaller, and especially we're running on those sizes which are much smaller because of the cost of inference behind them. You have to know in 2021, the models which were state-of-the-art goes from GPT-3, Jurassic Gopher, and by the way, this is the pre-era of GPT, ChatGPT, I'm sorry. And so for people who are in the domain, of course, GPTs were known, but the chat version, which everybody knows, came basically at the end of 2022. And of course, if you see the size of the model, they're quite big. Only a happy few can run them. We're talking about a model with 530 billion parameter, as you can see here, trained on 270 billion tokens. And of course, a big paradigm changed on the development of these models because a paper, which was quite important, done by Kaplan et al., showcased that in fact, when you build models, of course, the size matters. The more the parameters you have, the better it is. But in fact, there's two other features that when you build models are important. It's the data set size and the quality of your data, and the number of computes or the number of time you run those models. If you play with these three features, then you can build a model which has lower number of parameters, but if you increase this and this, you'll have a model which works quite as good as the big models. And so, of course, this led in the year 2022, 2023, to a series of models that we've been seeing even in 2024 of sizes which go up to 3 billion, which is what we have with Llama, and extremely good performance because people have been spending time on making the data set extremely good and clean. And also, if you take Llama 3, for example, big with 15 trillion tokens, and the number of epochs that they've been running is up to 6. So this is quite an important feature because, of course, it has pushed the community to start building models which are of smaller size. And the main reason is, of course, because we want the people to be able to use them on their laptops, up to that, in how you compute around those things. Now, of course, even with that, this does not come for all the people to build these models, which we call foundational models. And I want to insist on that because what we're seeing is that there's only happy few which are building foundational models, and then other people which are more affordable, which are basically fine-tuning them. There's a nice paper called Choose Your Weapon, Survival Strategies for Depressed AI Academics. And the paper says exactly the situation where academia is today, in the sense that the fact that we can't have access to a huge amount of compute cannot let academia move forward in terms of building foundational models. Of course, the paper, if you have time to read it, it's on archive, explains, of course, different strategies that you can play with, meaning that you can work on theoretical stuff and other aspects. But I think one of the main conclusions of this paper, and I think this is a good opportunity here in the talk that I'm giving, is the fact that academia and industry should work closer, where basically industry should start providing more and more the platforms for academia to start training and trying their ideas. Because again, from my point of view, the smartest people I know in the field are in academia, and these people are willing to stay where they are if you provide them the right environment. And I think this paper also showcases the kind of way of going it. I talked about, of course, training those models. On the inference part, it's also a big issue. Only few companies can also support the fact that people can use those models. And using those models means you can serve them. And when you serve them today, a request that you're doing on Google or ChatGPT, you have a factor of 10 in terms of cost, which means that we need to work to make these models more ubiquitous to reduce the cost of serving. And one of the, of course, strategies that people are looking at today is to make specific hardware just for doing inference. And I think the big thing that's going to come in the next 2 years is coming, of course, on architectures which are extremely fast and extremely energy efficient so that we can lower the cost. And here you have it here based on some surveys which I've been doing, where basically GPT-4 costs still more than having basically a person behind the phone in terms of answering basically your question. So that gives you also the kind of points. Now, a couple of things also on the Gen AI, which is quite important, and I think also I want to mention them. The first one is the energy consumption that is going a bit wild today in the AI sector. These are projections from a paper called Situational Awareness, which are projecting basically by 2030, basically, the fact that these Gen AI techniques and models that we're building will consume nearly 20% of the US electricity. So it poses also a big issue today if we want to be sustainable, and especially in our sector, on trying to find ways to solve this case in a very easy manner. Of course, research is at the heart of that. And I think we need to push more and more of our researchers, especially also the people working in the telecom industry, to start building ways of doing more efficient training related to that. There's a nice paper called Addition is All You Need. You remember I talked about computing is all you need, attention is all you need, which looks at other ways of computing rather than multiplication, because it's at the heart of everything you do, and looks at how doing just additions in some ways can make the system of training more energy efficient. I think we'll see more and more papers of these type running. Second thing also, for your understanding in the Gen AI field, which is important, is the data. In the same basically type of analysis, people are looking basically at the fact that we will not have any more data around the dates of 2027, 2028. One of the main reasons is that, of course, people are writing less and less on internet. And they're writing less and less on internet because they're using Gen AI tools. And what happens is that, of course, we're seeing a prolific number of data sets which contain Gen AI tools. Many of my colleagues are not anymore writing on LinkedIn. It's AI which is writing the post on LinkedIn because they're helping themselves. Emails are not written by humans anymore. Recommendation letters, by the way, in academia, often today are basically done by Gen AI. And so the question is, how are we going to go forward? It turns out, of course, that I've been working on that. If you decide to train your system on Gen AI data, you have something which is called a model collapse. So it means that we have an issue because the data that is being gathered today, well, has an issue because once you train it, you collapse. And it's normal because you cannot learn on yourself at one moment on your data. And so the question is how you can start creating synthetic data, which is not Gen AI data, which can still scale, which is a big issue related to that. I think this is going to be a very interesting topic, especially for the people who are working in telecommunication with digital twins and other things like that, to start, of course, creating synthetic data, which enables us to go forward related to that. So I give you a bit of an overview. I spent time, I'm sorry about spending so much time, but it was very important for you to understand the Gen AI revolution. The second revolution, which was important for you also to kickstart understanding, is what happened in 2023 within basically a revolution called 6G. I would set personally the date of 6G in 2023. Of course, it started before, but you have to know before, there was still not a very clear kind of consensus worldwide about if there was going to be one standard or multiple standards. And in 2023, we were very lucky because ITU, WP, 5G agreed on the IMT 2030 framework. By the way, 6G is a marketing term. IMT 2030 is the right term. 5G is a marketing term. IMT 2020 is what people use. Just for information, everybody can stamp anything they want within 5G and 6G. And so they agreed on that, and they came up, of course, with some of the requirements that are requested by that. And second, also big event which happened in Dubai at the end of 2023 in December is basically what we call the World Radio Congress. In Dubai, more than 1,500 people gathered with 150 delegations discussing basically the allocation of frequencies that will be discussed. And I think these two events were really the kickstart of that. And of course, with also what many of you are seeing today are on the KPIs that we're requesting around 6G. Here you have, of course, the documents that I extracted from that, where instead of going from a triangle, we go to an hexagonal now with different requirements related to that, but also some key requirements that you see here related to the peak rate, which is 1 terabit wireless, the kind of energy efficiency, and other things like that that are requested by next generation type of platforms that we want to do. Within that, of course, there are several technologies which can fulfill that. And my goal here is, of course, to talk about the Gen AI one. But just for your information, if you're interested, today what we're seeing as potential candidates, as technologies that could be pushed within the realm of this 2030 deadline, can be cast into 3 categories. I should put them, by the way, in 6 categories because you remember the hexagonal, but you can summarize them in 3. On the first set, what we're seeing people pushing as technologies are these ones. On the broadband connectivity, you have things like holographic MIMO, terabits coding, OEM, cell-free massive architectures, large intelligent surfaces, millimeter wave, LEO satellite, beyond OFDM waveforms, ultra-massive access, and time reversal. On the sensing and control, you have, of course, joint sensing and communication waveforms, terahertz communication, wireless imaging, extreme RLC, age of information, and beyond sampling. And on the intelligence part, you have things like AI transceiver, multi-agent generative AI, distributed GPT, edge learning, building semantic source code, and also semantic channel code. I'll talk about the intelligence because that's exactly what I'm interested in now at the moment. To build that intelligence for the telecom domain, well, we've been working on this telecom GPT pillar, which are of 3 types. The first one is, of course, building telecom foundational models, knowledge-based, and basically building them such as they are small enough so that they can run on devices. There you have 2 approaches. One is to take a foundational model which is big and then quantize it to make it capable of running on a device up to the IoT. In general, you lose a bit of performance. Second is to build basically a large language model by taking the low precision AI of our architecture at the heart. This is called pre-processing. And this requires some new thoughts on how you implement basically a gradient descent. Because if your weights, for example, can take only 0 and 1, then you cannot do a derivative anymore. So you need to rethink the problem of learning to a problem of combinatorial optimization to do it. And of course, a lot of my colleagues in the coding field are quite expert because it becomes a decoding problem. This is, by the way, called binary neural network. The second, of course, is building models which are suited to the telecom domain, not just about implementing them in IoT, but using the multimodality. In the telecom domain, we have, of course, video. We have images, but something also very particular is other type of signals that we gather, which are called radio frequencies. The problem is how you tokenize and you build them to bring them into reality. And the third one, of course, is the will to build up telecom autonomy and agents which interact to solve some problem and reconfigure exactly like the driving scenario that we're having. So on building this thing, we started basically, as I told you, and with the release that we made in July, a Telecom-GPT 0.10 type of model, which is a knowledge-based model, and I'll talk about it. We were quite happy because he made the press and there was a lot of announcement. That Telecom-GPT is basically based on a paper that we published on arXiv, which is fully available on the community, and with all my colleagues here that you can see who have been participating on it, and providing basically the kind of features that we'll talk about right now. For your information, of course, this is just a starting step. I am today the general chair of basically an activity within the ETI called the Large Generative AI Models in Telecom. We have a lot of partners coming from different companies, Huawei, Apple, we have Ericsson, we have China Mobile, we have many entities which are working all together here to start, understanding, building the data sets, building basically the benchmark to make sure that we create a community around these large generative AI models on what we construct. So what did we do exactly? What did we talk about Telecom-GPT? Well, we did three things. We started developing a telecom data set, very accurate for the telecom domain, so that we could pre-train and fine-tune our model related to that. Second, of course, when you build a model, you need also to define the benchmark. When we started, there was no benchmark in our industry in assessing what is a model and what it should do. So we built up also the benchmark, and then of course, we built up the training pipeline to build that Telecom-GPT model. And here you have the different step. We took all the data corresponding to 3GPP documents, ETSI documents, available documents that you can find on different websites of companies like Huawei and others. Then we did extraction and pre-processing, and then we started defining the specific data creation related to that. And I think that was quite important. You have here a training pipeline that we have been using, which I think is very instructive, with this open telecom data set that we built. Then basically the fine-tuning that you can do here, basically on this general purpose LLM, the instruct tuning that we worked on, and then the alignment tuning that we had to do to get this Telecom-GPT working as it is. Of course, you have here, and you can get more details in the paper, on the percentages of documents, how much we took, basically from code and things like that. And of course, this relates also to the benchmark on how we wanted to feature the model around that. You have also the number of GPUs that we've been using, the number of tokens that we've been using to pre-train, to fine-tune, the model that we had. And I think also that's quite important for all of you to see. Let's see now what it does. So there's a couple of things that you want from a knowledge-based model, okay? In terms of use cases that you want to solve. The first one is related to the queries that you want to do in telecom standards, research paper, and patents, where you don't want to spend your time looking at all the details, and you just ask the interface about something which is on release 16, for example. So here, typically what we ask, what does IAM stand for, and why is it considered desirable for constellation in communication systems? And you see here where it tells you, it identifies that IAM is index modulation, is desirable for communication system constellation due to its higher signal-to-noise ratio efficiency compared to conventional techniques, low complexity implementation, and compatibility with existing coding and modulation techniques. By the way, we compared, of course, the answer that we get here with respect to GPT-4, with respect to Mistral, and with respect to Llama. And you can see on the paper, the scores, we do much better than those models because, of course, it was fine-tuned on data over there. The second thing also that you want is explain techniques, identify problems, propose solution in telecom. So here, for example, we ask, but you could ask things which are much more complicated related to some features of your material. Describe the process of providing authorization to a mobile device for pending transaction request. And then you have the answer. To provide authorization to a mobile device for a pending transaction request, the system searches the database for the mobile device and it gives you all the instruction. Same thing, initiate event-based charging with decentralized and centralized unique determination, centralized rating, and it gives you the different steps. Request for resource usage, blah, 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 blah. Units determination, blah, 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 blah. Charging data request, so it gives you the instructions step by step that you should do, which is extremely important for people who are in the field and basically being able to do what we call field technician assistance, where basically you want to know how to do things. And of course, this can be done with voice, by the way, because in general, technician which are on the field just want to request some kind of feature that you want to do. But you have also things which are more, because we learned also in code. Things like analyze the script contribution to telecom workflow, specifying its primary functionalities, and we give here, as you can see, a code. And automatically the system tells you the script defines a function BSC for binary symmetric channel within the telecom domain. It takes input bits, array of bits, and PT transmit transition error probability as parameters, and returns blah, blah, blah. So it explains exactly the code that you've been doing. Of course, you can put the C code, you can put the MATLAB code, you can put the Python code. But you can also ask to generate some features of your standard, especially code. So here we ask it, develop a C function that retrieves and returns the transmit power value for wireless device. The function should update the data structure representing wireless request with the TX power information, and then you can generate. And so even outside the engineering domain, or also from an educational perspective, when you want to train your engineers in universities, this could be also a very good tool based on knowledge that we have here. And then what we wanted to do is also help the community which is doing research. And so what we did is basically ask the following question. Please fill in the missing mathematical equation represented by mask. So we erased all the equations of a paper. Placeholder in the provided section of a telecom relevant research paper that discussed the system model or problem formulation. And then we wanted to see if it could write down all the equation and understand basically the telecom paper. And this is what we did here. You see, we consider a discrete time zero mean jointly proper Gaussian flat fading channel with the following input output relation, and we put a mask. And it tells you y is equal hx plus n, xh plus n. Then we tell here, the channel fading process is zero mean jointly proper Gaussian with the temporal correlation characterized by, we put a mask, and then it writes exactly the right notation, and also the summable. I showed you here, it's mostly text only. You can do, of course, images also for our understanding, and you can go forward. So that was for the knowledge based. We continued, of course, on our journey, and this paper I think is quite nice, and I think you should take a look at it, which was published basically in July 2024, looking at RF GPT, meaning being able to input RF signals and be able basically to get some things. Of course, here the big issue is the data, getting basically the data which is related to different configuration between environment images and channel measurements. So you could do, of course, many channel measurements that you have in a given scenario, and of course provide the 3D layout. But in general, it's not enough, so you need to resolve to ray tracing. So typically, this is what we've been doing to be able to do what we call 3D imaging. And by the way, we're not inventing something new. My colleagues who have been working in radar know, by the way, that whenever you have a signal, then you can say a lot of the things on the plane which is arriving. What you want is to have a 3D image of that plane. And so in general, that requires a lot of data with a lot of pre-training, and that's what we've been doing through an image encoder, RF encoder, image encoder, RF decoder, and doing some kind of fine-tuned VLM for multitask sensing, which is at the heart also of the 6G key features that we have here. And what you do, of course, is signal to image and image to signal in terms of ratio. So in the sensing environment, this I think has a lot of potential. And of course, with the more and more data that you can gather related to different configuration, you can go around those things. And the last one I want to talk about is, of course, the work that we've been doing in the telecom autonomy and trying to build basically an architecture which enables, of course, to build what I call Telecom GPT 3.0, which is agent solvers. Because what we'll have today is a prompt where different agents are in different parts of the network, and you want them to work collectively to solve a given problem. So we did it at the moment just at the level of simulations, but I think it's quite interesting for you. We have a series of papers where we show how these LLM can be used as solvers or optimizers. So we have a paper called Diffusion Models as Network Optimizers, Exploration and Analysis, and Large Language Model-based Multi-Objective Optimization. And the idea, of course, that you want to do behind, and we've been working on it on a couple of papers, is basically that you want to give some instructions at the language level, and you want the network to be able to basically solve different features in terms of choices of frequencies that you're going to use, beamforming that you want to use, and things like that. And so this is very important from a large action model, because it's not anymore about just asking questions, but giving a request that you want in terms of making it. So in a given scenario, which is simulation-based, or here, there's no realistic system. It's mostly about simulation that we did. We wanted to have basically a system on where we request to solve the problem of energy efficiency of your network. So what we give as an instruction, we tell to the system that we want basically that we want the base station to reduce the total transmission power by 0.85 watts while keeping the rates of the users. So this problem is a bit complicated because in general, it depends on the model that you have, but you don't even need to model. You just ask with the prompt some instruction. And then as you can see, the system will iterate many times. And what's interesting is that at the end, the system is able to find the exact mechanism to find the power. Of course, this has been done in a very simplistic case. We are still working intensively with my colleagues today to try to understand basically how these LLM-based solver, of course, could be used in a broader setting for more scenarios, and the kind of course also of proof of convergence that you need on these results and reliability. But I think the future is going to be about providing LLM optimizers or AI-based solvers, because a lot of the tasks that we are aiming today is to give an intent to the network, and you want the system to run it and solve that intent that you have been issuing. And that's, of course, at the heart of these what we call self-driving networks, autonomous networks that we're doing, which is autonomy. I think I went into a very fast overview of the topic today of the fundamentals, one part, and the second part, which was more related on the application that we've been building around one vertical, which is the vertical of the telecom. Of course, for working on a vertical, you don't need necessarily to build a foundational model, because in this case, you in general take an existing model, but you need to do it carefully, and then basically fine-tune it, and that's what we've been doing to be able, of course, to enhance the performance of your network. I think you got now all the elements on the stage here related to the convergence of Gen AI and telecom, and I'm quite happy that you got at least an overview of what's going to be expected in the coming years.